Hello everyone, this is the explanation video of quiz 3. Now, the task is quite basic. We have a function called getMaxTau, and the input arguments are basically the body data here. You can use the body function in order to create basically the data here. So let me also open up MATLAB. So when we call body with magnitude, phase, and omega, we will basically get the data from a certain transfer function. And the task is to determine the maximum amount of delay that can be added to the system GS, which is basically the system that we are looking at the body of. And we're trying to come up with the maximum amount of delay that can be added to GS in a unit feedback structure so that it is basically reaching the stability bound. So this is kind of a dual problem to the p-type controller where we were looking for a gain and GS and a unit feedback, and we would then look at the body data and try to come up with a gain that causes this stability bound. But here it is about delay here. The function getMaxTau should basically use magnitude, phase, and omega data and come up with the tau value here. So if your function, if for example, for some reason, it's not possible to come up with such a value, you should basically return something like not a number or inf. One of both of these can be returned in case of the non-existence of tau. So that's also quite possible. And well, if your function works, you will get 70 points, and if you handle this error correctly, or if it's not available and you return it, then you will also get an additional 30 points. So when you are defining a transfer function like TF, let's define just one, 1,12, for example, we can use mag, phase, and omega, and then body, and then GS. So let me just fix that. So there we go. Now, what we are doing most of the time is we use mag equals squeeze. You can assume that this is the case, or you can just put this into your function so that you're pretty much safe here. So I would recommend you to put these two lines into your function, squeeze, and then phase like this, so that you get rid of the unnecessary stuff. You have magnitude, you have phase, and you have omega. So these are the inputs of this function, and this function should somehow return tau. And when we add tau to the system in a feedback, so you can check it out, if we have feedback and then GS times TF 1,1 IO delay, and then the amount of tau here, we should see basically a marginal stable closed loop. If we decrease this tau value just a little bit by like 5%, then we should get a stable closed loop transfer function here. So this is what the question is about. So you should calculate this tau, and you are not allowed to use any built-in function that can do this, maybe in MATLAB if it's existing. I'm just being safe here. So it should be just your implementation. So basic operations are necessary and sufficient to solve this problem, to come up with the tau value in a unit feedback structure that destabilizes or pushes the system to marginal stability. So yeah, this is also not a long function. I can give you the number of lines because I have solved it. With the function definition, it takes 18 lines of code, or maybe even 17 lines of code. So think about it a little bit, maybe research it a little bit in your notes, in your lecture notes. You should know what this means, and you should know how to come up with this maximum tau value. So good luck.